my yes.
Yeah, we can see it.
You cannot hear me?
We can.
Okay. Can you hear me now?
Yes.
Good. Wonderful. Okay. Good. So I will go yes over this file, yes, and I will explain this thing. So I think the title, the full title of the course is new applications, recent applications of cumulants in free probability, specifically in calculations with free random variables, right? So, but this lecture is about so showing cumulants, yes. So, and then there are of course, for free random variables we have the free cumulants. There's an established theory of that, and I will to some extent cover that, yes. But one of the points of my lecture is that besides the free cumulants, there are in non-commutative probability there are also these Boolean cumulants which are being used, yeah. And of course, this is all coming this is an analog of the classical theory, which is like 100 years old. Okay. And what I'd like actually to do is show, look at these cumulants, take a step back, yes, and okay, so there are these analogies between these three types of cumulants, and what makes that work? That's my I'd like to somehow discuss a bit. Okay, so what's going on here? How come that these things go in parallel? And I'll try actually to do play the following game. I will introduce all three of them at the same time. I will just talk about something which I'll call L cumulants, where L is some collection of lattices, and these three examples will be my main example of cumulants. Okay. Now let me also say also. So lecture one is really kind of basic stuff about cumulants, and I believe that many of the people either in the room or online know this already, but I try to do a bit of a different point of view so that it's not completely uninteresting. Yeah. Okay. And then for the other two lectures, here is a little outline of things that are coming in these other lectures. So one thing is I will. So my purpose is to show how cumulants are used for doing calculations with free random variables, and particularly there is this, so to speak, mysterious wisdom of the Boolean cumulant, because Boolean cumulants wouldn't be supposed to have applications to free random variables, yet they do. Yeah. So I'll discuss how the multiplication of free random variables is described nicely in terms of Boolean cumulants, and actually there is a whole continuous interpolation between Boolean and free, and I will discuss how those T-Boolean cumulants describe multiplication of free random variables. Okay, and then I'll move towards kind of explaining. So actually these T-Boolean cumulants, and also there is this other important brand of cumulants called monotone cumulants. Yeah. So when you try to integrate the monotone cumulants in the theory that I'm developing today, you start to use something which is called this framework of convolution in a lattice, and I will elaborate on that. Okay, and then there is a certain group of, well, I call them semi-multiplicative functions which play a role there. Okay. So that's one thing. So one theme of my lectures is this kind of like the fact that there are some other cumulants besides the free cumulants which somehow help with the study of free random variables. Okay. The other theme is the fact that actually Hopf algebra considerations seem to be important. Yes, and particularly this. this group of semi-multiplicative functions, actually, I think it's after you understand how it clicks, actually, it's the best way is to view it as the group of homomorphism of a certain Hopf algebra, which you construct. So it is in some sense like a dual structure, and it is interesting to study the structure itself, the Hopf algebra, for instance, because the antipode of that Hopf algebra is like a universal tool for doing inversion. Like with these cumulants and with moments, you know that all the time there is this issue of how to convert from cumulants to moments and vice versa. Mostly like vice versa is difficult. It's a Möbius inversion, and the antipode of the Hopf algebra promises to be like a tool which streamlines such calculations. Okay. Yeah. So that's how. That's what my lectures are kind of trying to do, yeah, or will try to do, yeah. And today, as I'm saying, it's like kind of going for basics, yeah. So I'll do as I'm saying. So my goal is to do a kind of a way of introducing the notion of cumulants, which can be, depending on what you want to have, can be the classical, the free, or the Boolean cumulant, yeah. And I start with notation, yeah. Okay, so we have partitions of sets of the form 1 to 3n, yeah. Okay, and traditionally the parts of such a partition are being called blocks. So pi is a set of subsets of 1 to 3n, which together give you 1 to 3n, and they are called the block, yeah. Okay, and very important, we have a reverse, so P of n. P of n is the set of all such partitions, yeah, okay. And we have a partial order by reverse refinement. We have a partial order by reverse refinement, and let me draw here. So for instance, yes, so say I make n equals 7, yeah, okay. And let me draw a partition pi and the partition rho. So let me do here 7 points, 1, 2, 3, 4, 5, 6, 7, and here is going to be my partition row. So I take the block 1 with 3 and 4. Okay, that's one block. Okay, and I take 5 with 7. That's another block. Okay, and then 2 and 6. They are my third block. Yeah. And let's say that this is my partition row. Okay, and then pi less or equal rho means that you take the blocks of row, and some of them whichever ones you want, you break them into pieces. Okay? So for instance, I take, so here I'll make pi. Yeah. So say in the block 1, 3, 4. I decide to keep 1 and 3 together, but put 4 apart. Okay. Okay. And 5 and 7, I allow them to stay together. Yeah. Okay. And then 2 and 6 say that I also allow them to stay together. I don't like. Okay. So here I just broke into pieces one of the blocks. Okay. So this is the fundamental partial order that we are using. Okay. The minimal element with respect to it is the partition into n singletons. The maximal element is the partition into one block. Yeah, and they are called that kind of customary to call them 0n and 1n. Okay. Yeah. Then another thing which I want to use quite a lot is this fact that there is a wedge operation. It's wedge or meet. Yes. Which is given to partitions, you do all the non-empty block intersections which you can do. Yeah, and then you get a new partition, yeah, which is called P1 wedge P2. More general, you can do this for any family of K partitions. Yeah, okay. And this is immediately seen as the greatest common lower bound of your family of partitions. Yeah, okay. So this partial order by reverse refinement has a notion of greatest common lower bound. Yeah. Okay. Now, actually, like it would be easy to see that also it has a notion of least common upper bound. So really, it is a lattice, but there is a distinction, namely that this wedge, the mid, this is kind of universal for all frameworks that I'm using, as opposed to the least common upper bound, which actually will turn out to be dependent on what kind of partitions I'm planning to look at. Yeah. Okay. So yeah, so then I'll go and I'll introduce this framework that I want us to look at. Yeah. Okay. And we'll take it from there. Yeah. So here is the framework. Yeah. Okay. So for every n, I take a subset L of n of partitions of 1 to 3n, yeah, and I'll start putting conditions on these L of n. I'll start putting the conditions which I know that make the various little proofs about cumulants work. Yeah, okay. So it's going to be a list. Actually, it's going to end by having 6 conditions. Yeah. I start like 1 and 2, yeah. So I want L of n to be stable under wedge. So these kind of intersections block by block, I want them to be there. Yeah. Okay. And then to have something to start with, I'll take the minimal and the maximal partitions to be in L of n. Okay, and I'll call this coherent family of set partitions. For the moment, there's no coherence because actually these are all conditions which are stated for the individual L of n's. But as the further conditions 3, 4, 5, 6 are coming, there's going to be more and more coherence there. Yeah. Okay. So anyway, so this is the kind of structure that I want to look at. Yes, this is my L. Yeah, which is the union of the L of n. Yeah. Is there a question or an interruption or something that I've done which I shouldn't have done, or no? I'm okay. Yeah, like yeah. Ping, are you there?
Yes, we are here.
Oh, good. Yeah. Okay. So I'll go on. Yes. So then okay. So these L of n, yes, they have. They inherit the order by reverse refinement, and also they inherit the operation wedge, because I postulated that they have to be stable under wedge. Yeah. Okay. Here is a comment, namely that actually really what's important for for a good chunk of the discussion, not for everything, but the discussion goes quite a bit like just by focusing at the one end. So 0n is less important than the 1n, and this is because actually even if you didn't put the 0n in, so you just ask for 1n to be there, still you would get that this L of n is a lattice. Yes, it will come very soon. But in any case, so right now you see that even if you don't ask for 0n, you get that there is a minimal element, because you can just take the wedge of everything that's in there. So you take the wedge of the complete list of the partitions from L of n, and you get a minimal element, yes, 0 of the ln. But indeed, then you could design examples where 0 of the ln is not the minimal partition 0n. It's something which puts some points together. Okay, good. So yeah, and now come the examples. Yeah, so what are the 3 main examples? Yeah, so one is when L of n is P of n. Yeah, this will give in the discussion that comes the classical cumulant. Then for a second example, L of n is the collection of non-crossing partitions of n, and I have a feeling that, again, most people at this conference are familiar with non-crossing partitions, but actually let me draw one. Yeah. So again, let's do n equals 7. Oops, 1, 2, 3, 4, 5, 6, 7. Okay, and say I don't know. Say that I put 4 and 5 together, especially that I messed the 5. Okay, and then I nest distance inside 3, 6. Okay, and then let's make a block with 3 elements, which is 1 to 7 and contains everything there. Okay, so 1 to 7. Yes, and this is an example of partition in. Okay, so my notation is a bit strange. Yes? So non-crossing partition of 7. Yes, and this is normally denoted as NC of 7. Yeah, this is how you see it everywhere. Yeah, I don't know. For this meeting, NC is kind of standing a lot for non-commutative. So okay, let's respect the non-commutative initials, and also it's nicer to have this calligraphic P for all kinds of or L or whatever, like calligraphic letters for all these sets of partitions. So I'm going with P non-crossing. Yes, this is the set of non-crossing partitions. Yeah, okay. And the third important example, the interval partitions. Yes, so these are partitions where every block is an interval. So these are very simple, and then in fact, yes. So I don't know if I do so again for 7. The only thing which you need to do, so if you know that the blocks are intervals, is if you indicate the sizes. So if you indicate the sizes of the blocks when you read them from left to right, then that's all you need to know to draw these partitions. Yes. So pretty much these partitions, these are ordered sequences of numbers which positive integers which add up to n. But anyway, so it's a very simple structure, but again, it's giving an example satisfying the conditions, yeah, that we want to follow. And these were the 3 main examples. Yeah, here, like I say, for didactical purposes. Yes, just like there are examples galore actually, but yes. So for instance, you could take L of n to be as small as possible. Just contain 0 n and 1 n. Or you could take here Ln is what you call a flag. Yes, like it is a collection of n partitions which are kind of in increasing order. So again, it's easy to see that well, obvious that this satisfies 1 and 2, and also they will survive a bit further, not all the way to the end. But so anyway, so these are didactical examples. Okay, good. Now let's make some observations which follow from my conditions 1 and 2. Yeah. So namely, so every L of n is a let. Every L of n is a let. Yeah. So there is a greatest common lower bound. That's obvious because I postulated that. Yes. So it's condition 1 was exactly, and so this operation of intersecting blocks gives the greatest common lower bound. Yeah. But then also there is a lowest guaranteed to exist a lowest common upper bound. So common upper bound, lowest CUB. Yeah. And how do you prove that exists? It's kind of immediate, right? Because given 2 partitions pi 1 and pi 2 in L of n, you take the set of all the sigmas which are at the same time greater or equal than pi 1 and pi 2. Yeah, quite important that this is a non-empty set. So and here it's important that we have 1n postulated to belong to L of n. Yeah. So you take this non-empty set of common upper bounds and you wedge it. Yes, and what you get is immediately seen to be the least common upper bound. Yeah. So it's a lattice. Every L of n is sure to be a lattice. Same trick as I just used also proves another little fact, namely that if you take a partition pi which is not in L of n, always there is a smallest possible sigma in L of n which bounds. Yeah, and this is called the L closure. Yeah, so every partition has an L closure in the lattice. Yeah, and this is the same argument where this time you take the collection of sigma i's which are greater or equal than your pi and take the wedge of them. Yeah. Okay. Okay. So now because this is a course exercise. Yeah. Okay. So yeah. So shows actually like there is something. So it's a trivial exercise. I mean, almost trivial. Yeah. But it's making some obvious remarks, but easy remarks, but good for taking this thing in. Yeah. So when you take any pi in P of n and start looking at its closures, the smaller is the lattice of partitions which you consider, then the bigger is the closure, which is of course right from the definition. The point is that these may not be equal to each other, and this generates some annoyance in various calculations. Yeah, and for instance, I can solve the part B of the exercise, namely I can draw here. So this if I make pi, so has to be 6 points. Yes, so I'll do 1 with 6, and inside here I'll do something which has a crossing. Yeah, okay. And then this one, if you look at its closures, then the non-crossing closure of pi, so P non-crossing. This will have to sort out those two things inside. So it will be this. Yeah. And if you take the interval closure, this is bound to be the partition with one block, because 1 and 6 were together. Yes, so they are different, and then this reflects if you go if you see at the look at the connection with the join. Yeah, so I said that there is a join which is guaranteed. It was here above. Yeah, so every two partitions in L of n have a smallest common upper bound, which is denoted as join sub L. And really, the L has to be there because, for instance, when you look at the join in the lattice of non-crossing partitions versus the lattice, the join in the lattice of all partitions, this may be different. Yeah, and that's quite annoying in various arguments that you run into, but it's a fact of life, so cannot ignore it. Good. So that was my background. And now I'm ready to introduce cumulants. Yeah. Okay. And the cumulants, they get to be introduced by using this moment cumulant formula. Okay. And I'll fix my L of n, yes, which has the properties 1 and 2. Yeah. But then let's also fix a non-commutative probability space, yes, which is taken in the most algebraic sense, yes. So just a unital algebra over the complex field with a normalized linear function. So I don't assume additional structure for what I need here, yeah. And the playground for all the considerations on moments and cumulants is this set of sequences of linear functions of multilinear functions. Yes, so this is an important, I don't know, fixture in my whole mini course. This M sub A, yeah, this Gothic M sub A. This is where the moment will live, and this is where the cumulants will live. Yeah, okay. And an element of M sub A is this sequence of of multilinear functional. So psi n is n linear. And one useful thing is that when you have it, you can always extend that. Yeah. So if you have m psi n, you can also have psi pi. So for instance, if I do say if I take I don't know this partition, so I take 1, 1, and 3 to be in one block, and then 2, 4, 5 be in a second block. Yeah. Okay. So this is a functional of five arguments, and then what I do is I put a product with a factor for every block. So 1, 1, and 3 were together. So then I do psi 2 of A1, A3. Yeah. Times, and then it was 2, 4, 5 being together. So this is psi 3 of A2, A4, A5. Yeah. Okay. So yep. So convenient notation. So there is a psi pi, yes, which is still a multilinear functional. So if pi is in P of n, then this is still an n linear functional, which collects arguments according to what the blocks of phi are saying. Yeah, I think I should well, I should have said that from the beginning. Like please pardon my terrible handwriting. Yes, this is a new thing for me. So yeah, I hope it is somewhat visible. Yeah, if it is completely non-visible, I would really appreciate if you told me that. Then maybe I can try something else. I don't know, but yeah. So can I go ahead with this? Yeah, well,
yes,
I will go. Yeah. Okay. So yeah, and okay. So here actually so far it only matters that A is a vector space. Yes, but because it is an algebra, and because it has a special distinguished functional phi on it, yes, then you have a special element in my collection in this special MA, the collection of phi n's, yes, which are just evaluating phi on products, and these are the moment functionals of A phi. Okay, good. So we have the moment functionals for my space. Okay, and then here is then the definition of L cumulant. Yeah, so remember that I am fixing in this section the lattice is L of n and the space A phi. Yeah, and there is a collection KL. Yes, KL is having KL n's and KL pi's. Yeah, okay. Such that every phi n, so every moment functional from here is written as a sum over cumulant functionals with index phi and with phi running in my lattice of choice, L of n. Yeah, and this is the basic moment cumulant formula. Yeah, this is my basic. Okay. And so this is called also like has some proposition in it because it asserts that there exists and is unique such a K superscript L exists and is unique. The proof is immediate because actually, if you look at this formula, if you separate, so L of n contains the partition 1n, and then if you separate that term is exactly Kn. Yes, so I can write that maybe here that so K, if I do the partition 1n, that's my Kn. Yeah. Okay. So then if I subtract, if I isolate this term, which is a Kn, and then subtract everything else, so it is phi n minus everything else. These are actually all coming from phi's of shorter lengths. So you can really prove both existence and uniqueness by some immediate induction. Yeah. Okay. Here you see, yeah, like for instance, yeah. So very yeah. for instance, this is how the basic moment cumulant formula works for n equals 2. Yes, because there are only two partitions for n equals 2, 0, 2, and 1, 2, and then you immediately then get that no matter what L we have, the second cumulant will have to be the variant functional. Yeah. For n equals 3, it gets a bit like longer, and it depends, right? I mean, if L is intervals, then you get a formula with 4 terms. If L is all the partitions or the non-crossing partitions, it's a formula with 5 terms, so different. Okay. And okay, so this formula, so this is the basic moment cumulant formula. Yes, so it's having like it is a bit of an inconvenience that here is just pi n, and this is written in terms of the k pi. So you'd like to have actually something more general, which also allows here for some phi pi. Yeah? And in order to write that formula, I know what the formula is because all the classical pre and Boolean cumulant satisfy it. But let me kind of dig into what makes that more general formula work. Yeah. And what we have to do is we have to add some more properties to our list. Yeah. Okay. And this is about this will be actually not so kind of like I think this is where the things start to be interesting, because you see some relevant properties that partitions may or may not have. Yeah. Okay. And it's about how you restrict partitions. Yeah. It's about how you restrict partitions. And let me let me take some examples. So I take my usual my usual thing with seven legs. Okay. Take my thing with my usual thing with 7 legs. Yes. So it's so this is pi 1, 2, 3, 4, 5, 6, 7, and I was doing 1 with 3 and 4. And then I was doing 5 with 7, and I was doing 2 with 6. So these are 2 and 6. Yeah, and these are 5 and 7. Yeah. Okay, and say that W is exactly having this 2, 5, 6, 7. Yeah. So I don't have to take W to be a union of blocks of phi, but for my discussion, this will be just fine. Yeah. Okay, so what you do is then you just focus on the set W, yeah, okay, and you see the pattern which is there. So pi restricted to W will be okay. So the pattern which appears is this, yeah, and this should be 2 and 6, and the other one should be 5 and 7. But I always ask that we relabel them in increasing order. Yeah, so this is how it the restricted and relabeled partition, and this is because actually my setting is so that I work only with partitions of 1 to 3n rather than working with partitions of general finite subsets of the natural numbers. That choice would simplify the things here, but would complicate them in other places. Okay, good. So now I can state what are my two more my two next properties. So it's stability under block localization and stability under block substitution. And let me explain a bit again. Like take this this example. So say I take my my phi and sigma. Okay, so again, like following the same. Pi is the one that was before. Oops. Okay, I think I'll do a trick. So this was a good experiment to do, but my skills are not up to to snuff. So I will do a substitution in the file which is being shared. Yeah, and I apologize for that, or maybe I don't know. You might find it funny. No, cancel this. I'll have to bring up this other one.
We can't see what you're writing. We can only see your face.
Yeah, I know, because I'm not sharing. But I will share.
Okay.
I will share in a second. Okay, so I will close this one. Maybe not. Okay, I will. Okay, let's make this a bit smaller. So now, well, my face is nice. I think like it's good to see a bit of my face and the fact that I exist. Yes, but now anyway, let me share. So I want to share this one. Application. Okay, and this was my practice file where everything seemed to be going so nicely. Okay, but I cannot do it live, it seems. Yes, so so see, here is where I was, and yeah, here I am doing. I'm sorry. So these are 3 done scribblings. Yeah. Okay, and you see here a pi and a sigma. Yeah. Okay. And what does this mean? So sigma is bigger than pi. In fact, I took my usual pi, yes, with seven dots, and which has 1, 3, 4, and then 2, 5, 2, 2, 6, and 5, 7, and I have put together 2, 6 with 5, 7. And this is the sigma, which now has only 2 blocks because 2, 6, and 5, 7 are put together. And then look what these conditions 3 and 4 are saying. Conditions 3 are saying like this: if you assume that both pi and sigma are in your lattice, then for every block of the bigger one, so for instance this block 2, 5, 6, 7, which was created, the restricted and the labeled partition must be there. So if pi and sigma are both in L of 7, then this restriction must be in L of 4. This is condition 3, block localization. So you take a block of the bigger guy. Okay. Condition 4 is somehow vice versa. You are only assuming that the bigger partition sigma is in your L, and you are assuming that whenever you take a block of sigma, so you take every block of sigma and break it, but in a way which is legal from the point of view of the smaller L. Yeah. So here there are 2 blocks of sigma which are broken, but this one 1, 3, 4 is broken identically. So that's automatically holding that belongs to 12.3. So if when you take every block of sigma and break it, so do block substitution suitably, then the result must be also in L7. Yeah. Okay. So these are the new conditions, which really requires some coherence among the L of n. Yeah. Okay. And these 2 things, as was clear from the example, are somehow converse of each other, and you can put them together. This lemma, this is an immediate statement which puts together the 2 things, those 2 stability properties. Yeah. Now they are phrased as some kind of a bijection between. This is an interval, right? I mean, the collections of pi's which are less or equal than a given sigma. This is an interval in L of n. Yeah. This is canonically in bijection with a direct product of such lattices. Okay. And now then I I can state my the extended moment cumulant formula. Yeah, so this is, as I promised, like it was originally it was phi n equals the sum of cumulant functionals. Now it is phi sigma. Yeah, so the special case when sigma is one n will retrieve the basic case. Yeah, okay. And what I'm saying is that with the new properties 3 and 4, this will hold. Yeah. And now, of course, now it would be interesting to actually look at the proof, because actually, like what I'm doing here for the whole lecture is this kind of situation, which I'm sure that everybody encounters every now and then, namely that I have a proof, and I want to clarify what's the statement which is being proved. Yeah, so I know the proof for this statement for either classical or free or Boolean cumulant. And what I wanted to figure out was what were the conditions which make the proof go. Yeah, and here is here is the outline of the proof. Well, so it goes somehow like this. Yeah, so you want phi sigma. Yeah, okay. You use the definition of phi sigma as a product. You use the basic moment cumulant formula. Yes, okay. Then you can switch this sum and product, and what you naturally run into is a summation over k tuples pi 1 pi k. And then you look a bit above here, and you see that pi 1 pi k from here can be substituted via this bijection used as the change of variable into a pi running in this interval, pi less or equals sigma. Yeah. So therefore, if I return here to where I had arrived, I can use the change of variable to convert this into a summation over pi less or equals sigma. Yes, and then there is some more work there to do to show that it's exactly the general term. But anyway, so the point was that indeed those conditions 3 and 4 and the lemma that I observed by putting them together, they are exactly what makes this work. Okay, so then I can now I conclude my section, which was introducing the cumulants. Yes, and my 3 basic examples give three families of multilinear functionals. Yeah, the classic the classical cumulants, the free cumulants, and the Boolean cumulants come from this basic example. Yeah. Okay. Yeah, I'm sorry that I'm not really succeeding to do my my plan here to show you like this is something which is very this is a very nice thing which I wanted to show you. So both for classical and for free cumulants, and also for Boolean cumulants, but that's kind of not really that much of an issue. So there is this super important formula for how you handle cumulants where the arguments of the cumulant are products. That's really fundamental for calculation. Yeah, and I can tell you the story that actually I like Speicher and his student Kravchik discovered this. So it was 2000, and they published their work about free cumulants. I think that at that time they were not aware that they are doing exactly the free analog of this Leonov-Shiryaev result from 1959. Yeah, and again here I'm looking. So okay, so again I have a proof. Yes, which is because it's kind of I think the same proof. Yeah, and I have a proof, and I want to know what's the statement, what's the condition on L which makes this formula work. Okay, and what I propose is that the property is a certain stability under thickening the line. So here are my here is a caricature of a where is it? Yes. Yeah. So what you do is you do the following. So formalize it like this. So take an m tuple of positive integers where the sum is n. Yeah. Okay. And then you have a thickening map, which takes any partition P in P of M and thickens some of the points so that it becomes a partition in P of M. Yeah. So for instance, say that pi is this partition with 3 dots. Yes. So 1 and 3 together and 2 separated, and then my J1, J2, J3 are 3, 4, 2. So then the first dot is thickened to 3 dots. The one in the middle is thickened to 4 dots, and the third one is thickened into 2 dots. But the blocks are still keeping together. So these groups of points still follow the same blocks as for the original pattern. Yeah. Okay. So there is this thickening, and then there is as a special case. It's this situation where you just take one of the points in 1, 2, 3, and you double it. Yeah. So take I and double it and make it become I plus 1. So again, this is my standard example, and I'm doubling 4, and then 4 becomes 4, 5, and this is a partition of 8 points instead of 7. Yeah. Vice versa, there is a map called merger. Yeah, merger map. Yeah. So this 4, 5, you merge them together to get back your pi. Okay. My conditions 5 and 6, yeah, are stability under doubling and merger. Yeah. Now, of course, it's clear that any thickening of points, you can achieve it by repeated doubling. So actually, if I ask for 5, then every thickening will keep me inside my family, my coherent family. Another observation is that any interval partition is a thickening of the 0 partition, because you take every dot and make it an interval. So asking this condition 5 plus the one that I had before, saying that the 0 partitions belong to the L, assures me that I have taken in the interval partition. Yeah. Okay. And here is I'm sorry that I'm going a bit over time, even though I think that still, because of my own clumsiness, I also started a bit late. Yeah. So coming back, so the 3 examples definitely satisfy everything 1 to 6. My didactical examples don't satisfy 5 and 6. But there is a thought which comes in connection to that, namely that all the conditions 1 to 6, these are stability conditions. And then if you have stability conditions, always you can define the generated structure. Yes, same as you define the Borel sigma algebra to be the sigma algebra generated by the open set or something like that. Yes, so take the intersection of all the possible families which contain some given S and satisfy the conditions 1 to 6, and you get a minimal family of L's which satisfy conditions 1 to 6. Yeah. So then this is presumably a source of examples. Like my didactical examples will both generate the interval partitions, but presumably there are more interesting examples which can come out here. Okay. And now I can tell you actually what I want is go and tell you the formula, and unfortunately I don't think that there will be time for discussing the proof, which again would have been interesting because yeah, this is that kind of thing that I know the proof and I wanted to find the statement. But anyway, so the key combinatorial point is that my assumptions make this maps. So this thickening of partitions from L of M, they are sure to go to L of N. And now there is this condition. Fact is that whenever I have a J1 JM, yeah, if I thicken to these sizes, whatever I do, so there is this smallest possible interval partition which is always there. So if I take alpha to be the thickening of 0, which is the partition with M blocks, where the sizes of the blocks are exactly my J of 1 up to J of M, yeah. Whatever I'm thickening with J1 JM will be greater or equal alpha. Yeah. So this condition is correct here. But the point is that because of my axioms 5 and 6, I can get this equality. Okay, and then with this equality in hand, we can prove this formula for cumulants with products as arguments. Yeah. Okay. And what's the kick in this formula? So I'll try to be done within the next 2 minutes. Yeah. We have our L satisfying conditions 1, 6. Yeah. Okay. We have our L cumulant functionals. Okay. And here is the thing. So we look at the cumulant of x1, xm. Yeah. But where each of the x's is a product of some other things called A. Yeah. Okay. And we record. So x1 is a1 up to ai1. x2 is a is coming from I of 1 plus 1 up to ai2, and so on. Yeah. Okay. And what I want is to write the cumulant of the x's in terms of some cumulant of the a. Yes, because actually this is extremely useful, because for instance a's could be some generators of the algebra, so finite set picked from a finite set of generators, while the x's are general elements of that algebra, general product of generators. Okay, so this is a very important formula, because it's telling you exactly what is the combinatorial structure which is being used for the description of this passage. So replace the products by commas. Yeah, that's the general idea. Yeah, so there is this alpha which appears. This alpha is the same as above, only that we have to be a bit careful. So these are the i's, yes, and the alpha was in connection to the j's. The j's are exactly the sizes of this monomial. So j2, for instance, is I2 minus I1, yes, and so on. Yeah, and alpha is that interval partition, and this is the condition. Yeah, okay. So it's very nice to see. So it was this last page, yeah, which I'm not. I think I can. What I can do. So this file is already online, and I can probably add some more details to it and rectify my horrible handwritten scribbling. Yeah. So there are some nice, well, three nice ideas which give this proof. Yeah. I think actually I don't want to go over time too much. Yes. So I'll stop here. Yes. So I do recommend to anyone who wants to actually kind of go into this business of cumulants, if you are not into that already, this is a great proof to look at. Yeah, good. So thank you.
Thank you very much.